Yeah, so hello everyone. If I'm audible and you can see my screen, please type Y. Okay, so it's 10:05, already 5 minutes gone. Let's start. So what we'll do today, we'll study. Till now, we have been focusing on the speech production mechanism. Today, we'll start with devote our time. Hopefully, we can complete it today to speech perception, and we'll discuss about something called the Mel Filterbank or the Mel frequency capsule coefficients, MFCCs, which are possibly the most important features used in speech processing for almost all applications. They are like the go-to features for any task you want to do in speech applications, in speech processing, whether it be speaker recognition, speech recognition, emotion recognition, whatever, voice pathology, doesn't matter. MFCCs are possibly the most important features in this regard, and it comes from speech perception. Its motivation is behind the science of speech perception. So first, what I will do, I want you all I've shared a link. It's around 3.5 minute clip. It is about the how human beings perceive sounds. So go through that 3.5 minute link and come back. Let's say it's 10:06. So by 10:10 come back, then we'll discuss. I will maybe also watch it from here, the same clip. So I hope you were able to watch the entire video. If you have finished watching, type Y. Yes. Okay. So now let's go to our topic for today. We'll close this window and start. So what we saw just now in that video was how sounds are perceived by the human ear. In this, that is the speech perception mechanism of sound perception, not speech, sound perception, which automatically means speech, music, and everything, anything acoustic. So what we saw was we saw that the sound is entering your inner ear through the external and middle ears. It enters the inner ear where the cochlea is housed, and the cochlea, it behaves differently. Inside the cochlea there is something called a basilar membrane. You saw in the video animation very well. I don't need to describe much. So there is a basilar membrane where low frequencies travel through a longer distance and high frequency travels a shorter distance. And basically the way the basilar membrane reacts to sounds of different frequencies enable further processing by the neural network and the brain. Now this part is much more complicated to understand, and probably not even very well understood. But till this part, the working of the basilar membrane, we know what's happening. And this forms the basis of the signal processing approach to encoding or extracting features from speech for different applications. So now going forward, so again, there are other things that we can look into. One is this loudness. Loudness is also a relative phenomena. So we have here analog frequency in hertz, and this is sound pressure level. So whatever you utter, somebody has uttered a speech, the pressure level, that is, it comes as variations of pressures in the air. That is what finally an acoustic waves. So you see now the sound pressure level, it is given in, it is described by a unit called forms. See, each of these lines is a constant loudness level. Okay, this loudness level is given in forms, not sound pressure level, sorry, sound pressure level in dB. Okay, so this loudness, each of these lines represents a particular loudness, but you can see for different frequencies you need different sound pressure levels. For example, here 50, let's say 50 hertz, and let's say some 1000 hertz. For 50 hertz, the sound pressure level has to be high in order to be perceived to be of the same loudness. On the other hand, for 1000 hertz, the sound pressure level needs to be quite low, but it will be perceived as equally loud. So many things in the human ear, that the and our brain also. So whatever we do as scientists and engineers and mathematicians, our signal processing and technology, the way we describe the phenomena all around us, that is not exactly how the brain and our biological systems work. They have their own scales, they have their own mappings, they have their own ways of dealing with stuff. Okay, so that is what we will see. So this is one another facet, loudness, that which varies with frequency. For different frequencies, you could have the same loudness depending upon, but with a different sound pressure levels. It would be this equally loud, 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 at different sound pressure levels and different frequencies. Okay, F1, F2, two different frequencies. If you have different, you need different sound pressure levels, but it will be viewed as equally loud. On the contrary, you can have the same. You can say also that the same sound pressure level, if you have two different frequencies, they might be perceived as equally loud. So the brain works differently. It emphasizes certain frequencies more, particularly the low frequencies, compared to the high frequencies. So next we come to this critical band theory of hearing. So critical band theory of hearing, this is quite important. Okay, so what happens is, we saw that the basilar membrane, it vibrates differently with respect to different frequencies, and these experiments were extended, and it was observed that the brain, the basilar membrane and the human brain in particular, because these are all linked. If we say 0 to 20 kilohertz is the range in which human beings are able to hear frequencies. Above that, only bats and certain mammals can hear. So let's say 0 to 20 kilohertz is our audible range, hearing range. This is about. So there are bands. There are certain critical bands around 24, 25, around 24, 25 bands are there, critical bands, in which the brain recognizes these frequencies and interprets them. So what happens is, for low frequencies, the brain is able to identify and those frequencies quite well from one another. So those critical bands, the bandwidth of those critical bands are less. But as the frequency increases, these critical bands, the bandwidth increases. Now, a very simple way to interpret this is, okay, let's have a sine wave. Okay, let's say, okay, let's make it very simple. Let's say 1 hertz. This is 1 second duration. So 1 hertz, that means 1 cycle per second. If you have another one, okay, if you have another one, this is 2 hertz. You can easily, from your naked eye, you can understand that. Just simply visually, you can say that, oh, okay, this was 1 hertz, above 1, the below 1 is 2 hertz. You can see from the diagram itself. Similarly, if I have 4 hertz, you can again be able to, okay, we can see what is happening. This one is 4 hertz, this one is 2 hertz. We can easily discriminate. These are low frequencies. Now, important thing to understand here is, there is only 1 hertz difference there. Again, if I take 4 hertz, there is only 2 hertz difference between each other. Okay. Now, similarly, instead of this, if I take 10 hertz and 20 hertz, you will be able to see the difference. You will be able to visually see the difference. Understand? Okay, above 1 is 10 hertz. The other one is 20 hertz, even though the difference is only 10 hertz. Now let's assume that you have a 1000 hertz sinusoid, and then you have 1010 hertz sinusoid. Now if I showed both of them, will you be able to discriminate which one is what? There is only 10 hertz difference. But will you be able to discriminate just by seeing the waveforms? Oh, which one is 1000 hertz, which one is 1010 hertz? Very difficult, probably not. But if you see, if I give you 10 hertz and 20 hertz, you will be able to quite easily discriminate. So this is a very good intuition on how this critical band theory. So we have these bands. That the brain processes these frequencies in bands, where the bands are small in lower frequencies, and as the frequency increases, the bands become wide. So this is called the critical band theory, and it is a proven theory, a critical band theory. So now in the brain, what happens is, there's a mapping taking place. It does not use our own the mathematics that we use to describe the physical natural world around us. That mathematics the brain does not follow. Or indirectly, another way to put it is that those scales they do not follow the Hertz scale. They instead of we describe things in electrical engineering in terms of amplitude. Okay, 1 volt, -1 volt, all that. They have a different way of recognizing things. So one of ways is this. So one of the important mappings for frequency, it's called the Mel scale. There are also some other mappings called a Bark scale and some others, but this one is the most used and the most popular that scientists have discovered or found. It's called a Mel scale. So what happens is just a minute. Yes. So the brain, while we describe the natural world frequencies in hertz and all, the brain does not do so. The brain has a different mapping. We call it the Mel scale. The Mel scale. So the Mel scale, in terms of the Mel scale, we have whatever Mel, the frequency in Mel is given by this equation. So frequency in Mel equal to 1127 ln, means log of e, 1 plus whatever is frequency in hertz by 700. It is also, I think, defined as 2595. You can also term is log 10 1 plus f hertz by 700. You can represent it as a natural logarithm or standard logarithm to the base 10. But this is how it is. So if you, let's say, confine yourself to around 4000 hertz, this is generally the region where most of the formants and vocal resonances, the speech spectrum is basically the speech spectrum is basically in this range. Of course, we can extend to high quality speech to 8 kilohertz. That means sampling frequency of 16 kilohertz. But more or less, this is the range in which most of the speech information lies. So if you put this, you will find in Mel, this is I think 2146 or 2150 almost, something around that. It will come. This is the mapping that will happen. Now, going forward, so what happens is we have talked about pitch. Because, as I said, the brain perceives frequencies in a different scale. We have all very loosely, in many ways, we have called the term pitch. And we have said that the pitch frequency and the fundamental frequency, they are the same. Means we have used these words interchangeably, but actually it is not. Pitch is a subjective quality. The brain, it is a quality of this brain's frequency scale. Okay, it is not. Whereas when we say fundamental frequency, we represent it as hertz, and we very loosely we use both these terms interchangeably. But in reality, pitch is a subjective thing, and it is best described in terms of Mels. So if somebody is perceiving some Mel as suppose 20 Mel, and he doubles, he's hearing another Suppose somebody is hearing a single tone, pure tone, okay, pure tone, that is a sinusoid at 20 mils, and there is another tone he hears that he says that it is almost double of that. How he perceives it's a different thing, but he or she perceives it different. But he says, okay, it seems that the new sinusoid, new tone that I am hearing, it seems like double the frequency in my brain. But that will not be exactly your 40 hertz. That will be related to this scale. Okay, 20 mils will be correlated to something in hertz, and 40 will be correlated to something in hertz, and it will certainly, so the difference 20 mils will not be equal to 20 hertz. It will be given by this equation. What it come, that is how it will come out. So this mapping and the critical bands, they are important for signal processing engineers to incorporate, so that we can get the appropriate features for various applications. And these applications vary. Means, as I said before, it's a wide range. Means what we'll discuss, MFCCs, they vary a wide range of applications. In fact, nothing in speech processing, area of speech processing, works without MFCCs. So let's go forward. What we have, so we discussed about critical bands and discussed about loudness and the perceptual scale, MEL scale. So now, so what do we do? So how do we go about these extracting features and from the critical bands and so on and so forth? So what we have found is, now this is the MEL scale. Okay, but this is the MEL scale. So the way signal processing engineers will incorporate it is, whatever MEL scale, let's say 4 kilohertz, generally up to 20 kilohertz, we have said that there we have noticed around 24 to 25 critical bands. But we don't, for signal processing purposes, we are not really considered about this 20 kilohertz thing. Okay, for us, let's say, we'll say whatever range you are picking, it could be 8 kilohertz speech or 16 kilohertz speech. Let's take 8 kilohertz speech, which means 4 kilohertz is your maximum frequency. Okay, so in MEL scale will be, I think 2146 or something like that. So we generally, the process is, this is what we do. We'll divide this MEL scale into equal portions, equal bands. So, and this number of bands generally are around 20 bands, or 20 to 24 around. This is the number of bands we take. This is what we have found to be useful in signal processing purposes, based on the concepts of critical bands and all that. This one. So in the MEL scale, not in our analog scale, we divide in terms of equal bands. So what will happen when we remap that? We'll find that obviously these bands, they might be equal in the MEL scale, but as the MEL scale increases, frequency in the MEL scale increases, the analog corresponding analog frequencies are getting wider and wider, getting bigger and bigger, because there is a non-linear relationship, there is a logarithmic relationship. So these are your bands in your analog scale. Whatever equal bands you created in the MEL scale, this becomes non-equal, non-uniform bands These are the uniform bands in the male scale. These become non-uniform critical bands in the analog scale. So now we have a concept called masking. Okay, so maybe I will give you an assignment. It's a simple assignment. Maybe you can uh, uh, do it as an assignment, go through it. So what happens is there are two types of masking: temporal, that is in time domain, and in frequency domain. Temporal masking and frequency domain masking, time domain masking and frequency domain masking. Okay, so whenever you have a speech sound, that is whatever you are saying, we, whatever, it's a, the speech signal is a collection of sounds basically. So whatever sound is there here in a particular short duration, it tends to what is called overlap with the sound that is after it, coming after it, and the sound that is coming before it. There is overlap. So speech is not like a disjoint collection of sounds. When we speak, see, the letters of the English alphabet are isolated sounds, kind of. But when we speak in a continuous word, the sounds merge together and give a different, quite a different overall speech sound, so to say. Means in a very, probably I'm not making a very, not putting it in a very good way, but I hope you understand what I'm trying to say. So this is called temporal masking. On the other hand, a particular frame, or a particular subframe, if you want to say, a particular sound that is being uttered at a particular short duration of time, it overlaps, it or masks the sound that is coming before it and after it. This is called temporal masking, and this occurs differently for different categories of sounds. So there is variation in that. The other is in frequency masking, where if you take the spectrum of a particular uh, speech signal, okay, or let's say, let's take the mel scale and its corresponding analog scale. So there are a frequency, a particular frequency. What happens is it masks the frequencies. It has an effect on the frequencies higher than it and lesser than it. A particular frequency has a masking effect on frequencies higher than it and lesser than it. So this is called frequency domain masking. So now how do we incorporate all this? So what we do is, all this information, how do we incorporate? So what we do is we have, we have found that if we divide the mel scale into equal regions, let's say 20 to 25 depends, then really people choose around 24 is generally the number people choose. In 24 equal bands in the mel scale. So correspondingly in the analog scale, we'll get this, something like that. So we get bands like this. Let's denote it as m equal to 1 or m equal to 0 and some, let's say m minus 1. It is a last band, let's say. So each band will have a center frequency. So what we do as signal processing engineers is we put a triangular filter, because we have seen, because of masking, that a particular frequency masks the frequencies higher than it and lesser than it, and we have again critical bands. We have critical bands, and these critical bands, I forgot to mention, they are not like disjoint, they are overlapping. Okay, they are overlapping. So because they are overlapping, we choose the bands like this. You first divide into 24 equal disjoint bands, then we get all this. This is, let's say, f0, f1, f2, let's say f3. Okay, so this becomes your, the first band is this, the second band is, or the zeroth band is this. The second band starts from the sorry, the first band starts from the previous band's, the zeroth band center frequency, to the first band's, sorry, the second band's center frequency. Oh, what am I saying? Am I making some mistake? No, no, I'm not making mistake. It's okay. I got you. So again, so what happens is, this is the center frequency now. I will probably give a better diagrammatic description of this. Let's look. I have a better diagram than me drawing and struggling with it. Okay, no issues. I have the, probably have. This is a diagram I will be taking where I think I've shared the books. A book, maybe Introduction to Digital Signal Processing. There I should find it. Where is the diagram? Yes, here. We should get a better view of this. Should be here. You can see I have taken most of the material from this book, so it is easier for you. Okay, I will give you a good diagram to match this to help you understand. Yes. So this is the way to do it. Basically, I forgot almost. So this is the way how you do it. I hope you are seeing the figure. So what we are having is, we are having these different colors are showing the different critical bands and the filters that we put it. Basically, we are putting triangular filters because we saw that there is an effect of masking, and masking, what it does is it influences, it subdues the frequencies near it, and this effect of subduing the frequencies near it is stronger as the frequency increases. Okay, so frequency diverges or is farther away from its focal point. Okay, so in critical band we take a central frequency and then we put a triangular filter on it. So how do we get the critical bands? Is that we have we divide the Mel spectrum equally, then map it to the our analog spectrum. Then for each of them, we get your what you say? You get the center frequency. So once you get the center frequency, then you just once you so this is your center frequency, this is your center frequency, this is your center frequency, center frequency, center frequency. So this is the center frequency of the first band, F3, F4, and so on. So you'll put a triangular filter like this. So obviously you can see the slope of this line is different for any one you take. For let's say take this band, okay, and we said the critical bands are overlapping, they are not disjoint, because the basilar membrane is what is called biological our human ear is a biological system. It is not like some NOT gate or AND gate. So things in analog systems, in natural systems, are generally overlapping. So we designed it like that. Signal processing engineers, we designed it like that. We take these center frequencies, and these center frequencies not only give us the bandwidth of any particular band, they also let us determine what should be the slope. Indirectly, what is the weight I am giving to a particular frequency in a particular band. So this is how we put different triangular filters over the critical bands. In the analog frequency scale. Now, once we do that, there is a process. There is no time today, but we'll discuss next class. There is a process, a simple process, through which we'll get the MFCCs or Mel frequency capsule coefficients. We'll discuss that next class. Please give your attendances, and that's it for today.